Hello everyone, today I will present you a paper written by Paul-Éric Dossou, Pierre Torregrossa and Thomas Martinez at the icam Grand Paris Sud about Industry 4.0 concepts and lean manufacturing implementation optimizing a company logistics flows. Building on the legacy of the three previous revolutions, Industry 4.0 has now introduced a new paradigm where continuous variations of requirements and the versatility of customers have a real impact on the company performance, which leads to the need for enterprises to adapt for producing and offering a broad variety of products. Thus, flexible resources, including human resources, need to be allocated to value-added tasks through the automation of non-value-added tasks. This paper aimed to test a sustainable digital transformation methodology for SMEs by the studies of use cases in an electronic workshop. Those use cases focus on the automation of non-value-added tasks related to storage and procurement of components and final products inside the workshop through Industry 4.0 concepts such as autonomous mobile robots, IoT, and artificial intelligence. First thing to notice is that the storage and procurement are zero or even negative value-added parts of the overall manufacturing process. Because of its accident-causing nature, it often ends up with human accidents or loss that results in extra cost management and delays. Indeed, repetitive actions for operators in stock management processes leads to lack of vigilance, ultimately causing lots of waste that can be avoided. Lean manufacturing thus gives us tools to eliminate those murders and avoid accidents. For example, DMAIC, 5S or Plan to Check Act contributes to continuous improvement together with the implementation of new technologies. In particular, standardization and automation are powerful means to reduce cost of non-value-added tasks through the definition of storage standards and the use of AMR for logistic flows. This is, however, where SMEs usually meet breaks for the implementation of new technologies with smart manufacturing and Industry 4.0 concepts, considering the investments and the integration process within the organization. This is why we developed a framework for optimizing industrial performance of SMEs based on lean manufacturing and GRE methodology developed by the University of Bordeaux together with DMAIC and design of experiments. The support strategy that we suggest consists of three steps. First, the evaluation of the current state of the company, then the definition of its desired future state, and finally the improvement of an ideal model of sustainability with feedbacks on the implementation of use cases in the company. Note that all the evaluation and definition is done in accordance with key performance indicators derived from quality, cost, delay, social, societal, environmental, and degree of modernization criteria. In the end, the main hypothesis that we test with this framework is that placing humans at the center of implementation of Industry 4.0 concepts and smart manufacturing method will increase industrial performance of SMEs. For example, automating logistic flows with AMR and artificial intelligence within the workshop while reducing stocks between workstations with an intern just-in-time strategy also offers the opportunity for operators to work on really productive tasks and potentially reduce health risks as well. On another level, IoT and big data can help optimizing energy consumption of the company through predictive maintenance use cases. And also augmented reality tools can be developed to assist operators in maintenance or stock management applications in order to reduce cognitive fatigue while certifying quality of the processes and thus avoiding breakdowns and other wastes. In this paper, we focused on the automation of non-value-added tasks related to storage to test acceptability of new technologies, such as AMR, with this framework among operators through use cases with an electronic card production company. Here in particular, the acceptability is supported by the development of a user-friendly human-machine interface for the MES. This aims to simplify management of logistic flows for operators with optimization and decision support modules based on artificial intelligence. For instance, expert systems can be used to detect points to improve in a process. Machine learning and deep learning can then be used to predict future flows and need of procurement for big data. In the end, the application should provide compiled data with relevant key performance indicators so that users can allocate cognitive resources to really critical decisions. In our case, the use case extends to the development of a stacker crane for input and output flows, standard bins for transportation of the components and products, a trolley to transport components and products between workstations and the stacker crane, and finally an AMR fleet to transport the trolley and manage fabrication orders according to the MES directives. This can derive to the layout as follows. First, an AMR can pick up the trolley filled with bins of components from the stacker crane, then transport it to the workstation depending on fabrication orders coming from the MES. Later, either an automated workstation or an operator will report the end of a process so that an AMR can come to pick up the final products and store them in the stacker crane. Here you can see the design we chose for the stacker crane. In particular, the use of rails on the upper part of the trolley allowed us to avoid the need for an input conveyor, thus gaining space for the bins of components and final products. About the trolley, the design is inspired by other systems developed by Omron or Skoda. However, we chose to separate the trolley into an upper and a lower part using another rail system, as you can see here, so that the AMR can simply drop the bins in the stacker crane with the upper part and then immediately go to carry out other tasks with, for example, with an operator, without having to wait for the storage process in the stacker crane to end. The AMR itself benefits from 6 laser scanners. You can see here, and there, for example, for calibration and safety purposes. By the way, other subsystems such as a Hall effect sensor to detect presence of a trolley might be necessary to validate the gripping of the trolley. Those constraints actually might have to be taken into account for the design of any other type of carts that need to be carried by similar robots. Finally, the AMR usually have several calibration methods. In this case, we have calibration by magnetic band and calibration by triangle detection. Especially for stowage use cases, magnetic band offers the required precision to the 1/10 of a millimeter. However, this better applies for static workstations since the magnetic band has to be placed on the ground. For other use cases, method with triangle detection can be used. In particular, this approach is very suitable for picking up a mobile trolley. Here you can see how the triangle detection method applies to the design of the trolley. In the end, this approach presents very low risk of failure, making it repeatable enough to ensure implementation in real conditions. However, it was observed that the quality of the ground surface influences the time it takes for the robot to pick up the cart. Indeed, scratches and stains, as you can see here on the ground, can be interpreted as obstacles by the program. This issue might be faced as break in the evaluation of the current state of the company. Thus, the emphasis should be on integration of 5S method to overcome the problem. Finally, we tested the stowage of the trolley in the stacker crane without the use of a magnetic band, which only gave us a success rate of 1 in 2 chances. Actually, this was later fixed still without magnetic bands, using a more flexible guiding approach. Indeed, with a one-side contact surface rail and the help of an electromagnet to ensure stability, we were able to improve repeatability of the process. Next steps about the use cases of the stacker crane include the improvement that we made and that has been tested for the storage and which could ensure repeatability of the process. For the company, future state will be checked after implementation of the use cases to test hypotheses about the framework on storage and acceptability problems. Currently, they are working on their establishment on a new site that will integrate those use cases among others. Furthermore, in a more global view, development is still in progress for the Intelligent Digital Transformation tool. Also, a demonstrator in Industry 4.0 is being implemented at the icam Grand Paris Sud that will include production lines for electronic cards and small robots. This way, the demonstrator will implement Industry 4.0 concepts and the sustainable framework.